Welcome back everyone. So in the last class we were discussing about the operation of DAB. First we have started with our simplified analysis where we were considering the primary side bridge to be in the picture and we were bypassing the secondary side bridge. Then we have added the secondary side bridge and we have bypassed the load, or we were considering the output terminal to be short circuited, and we have seen the effect of the delta. When delta was 0, the 0 power was transferred. Then we have increased the delta gradually and we have observed that from 0 to 180 the power transfer would be positive, and it is maximum when delta is 90. And similarly from 180 to 360 we observed that the power flow was negative, that is from the V2 to V1 side the power was flowing, and it was maximum negative when it is at 270 degree or minus 90 degrees. So from 0 to 180 and 180 to 360 we will have positive and negative power flow respectively. Then we have started our discussion with the actual loading condition, where we have assumed one example that the input side voltage, that is V1, is given as 400 in this case, and we have considered the V2 to be 800 volts. Okay, and we had started our discussion on seeing this DAB operation. So how to analyze this type of questions when we will have the actual loading conditions? First we have to eliminate the primary side bridge, then we have to eliminate the secondary side bridge, then we have to, based on where we have considered the leakage inductance or the external inductor which is present, we have to eliminate the transformer. Then we will be able to find out the voltage applied across the inductor, and based on whether there is a positive voltage, negative voltage or zero voltage, we can see the change in the inductor current. So here we have assumed delta to be 45. With that we have derived the gate pulses, and we are operating in the single phase shift mode, where the bridges will be operated in complementary manner, and there will be a shift between the primary and secondary side voltage generation, that is given by delta. Here we are assuming that to be 45. Okay. So here if you see S1 and S4, they are on for 50% of the time. For the 50% of the time they are bypassed, and the complementary switches are S2 and S3 on the primary side. Similarly, S5 and S8 are operated for 50% of the time, and the complementary switch are S6 and S7. Okay. So when this S1 and S4 is on, we have seen that the input voltage will be applied in the positive side, that is VAB will become equal to plus V1. When S2 and S3 are on, it will become equal to minus V1. Then we were successfully able to eliminate the primary side bridge. Then on the secondary side, whenever S5 and S8 is on, we have seen that the V2 voltage will be applied as plus V2 at the secondary side of the transformer, or the potential between these 2 points, or Vs, will be equal to plus V2 when S5 and S8 are on, and when S6 and S7 are on, it will be equal to minus V2. Now let us see one by one. So for the first case, or the first combination, where S1 and S4 is on the primary side, and S6 and S7 are on the secondary side. So on the primary side we will get plus 400 in this particular example, and on the secondary side, as S6 and S7 are on, so we will get minus 800. Then for the second combinations, where S1 and S4 is on the primary side, but we have shifted the pulses from S6 to S7 to S5 to S8 on the secondary side. This is true for the next 3 divisions. Okay, so for these 3 divisions, if you see, on the primary side plus 400 is generated, why S1 and S4 are on, and on the secondary side plus 800 is generated because S5 and S8 is on, and it is valid for the 3 divisions. Then after that we will have one switching on the primary side, that is we are turning off S1 and S4 and we are turning on S2 and S3. During this case, the primary side voltage will now shift from plus 400 to minus 400, whereas on the secondary side still S5 and S8 are having the pulse, so it will be maintained at plus 800. Then in the last case, where we have switching on the secondary side bridge, we have now removed the pulse from S5 and S8 and we have given the pulse to S6 and S7. So we will get minus 800 at the output side, and on the input side it was minus 400 because S2 and S3 are on. Okay. So in this way, what we have done till now, we have found out the switching combinations and we have eliminated the primary and secondary side bridge. Now we are left with the transformer and inductor. Okay. So, our aim is to find out the voltage across the inductor so that we will be able to find out the current, assuming that it starts from an finite negative value, as we are interested in the steady state operation of this converter. So, these are the 4 combinations which we have seen. Now, if I want to eliminate the transformer, so which side has to be the voltage shift should be taken care of. So, in this case we are assuming the inductor to be present on the primary side. So, I will find the reflected secondary voltage, or because of this 800 plus or minus 800 which is applied across the secondary of transformer, what will be the voltage on the primary side by considering the turns ratio to be 1:2 as per the given example. So, in this case, in the first case, the dot is negative. So, the primary side dot will also be negative. So, Vp will become equal to minus 400 because 800 will be divided by 2 when I take it to the other side. Similarly, in the second case, plus 800 will be maintained as it is. So, the dot is positive. So, the other dot will be positive. So, it will become plus 400. And in the third case, again we have plus 800 on the input side. So, it will be reflected as plus 400 on the primary side. In the last case, we have minus 800. So, dot is negative. So, the other dot will also be negative. So, we will get minus 400 as the reflected voltage on the primary side. Now, by this analysis, the 4 equivalent circuits which we have found out, now we have also eliminated the transformer in between. So, now our final step is left. We have to find out the voltage across the inductor by applying KVL. Okay. So, we will take them each one of them. Okay. Now, first case. Okay. So, when this was true for the first division. Okay. So, in this first division, what will be the voltage across the inductor? If I write the KVL equation, it is traveling in this direction, suppose. So, it will be plus VL. Now, we are traveling in this direction. Okay. So, it is equal to plus VAB minus of VL and plus of Vp is equal to 0. Okay. So, why it is minus of? Because this is the polarity of VL which we have assumed. Okay. Sorry, it should be the opposite way. So, this is the polarity of VL. So, when I apply KVL in this loop, I will see that I will travel through a, this is plus over here, this is minus over here. So, it will be plus Vp, then the second term which will be coming as minus VL because I am traveling towards the minus terminal first. So, I will write that as minus VL, then I am entering through the positive terminal. So, I will write it as plus VAP. Okay. So, if I simplify that, I will find that the voltage across the inductor will be equal to VAB plus Vp. Okay. So, we are traveling in this loop. Okay. So, and as per the signs which are coming to us at the first place, we are consuming that to be with that polarity. That is, when we are traveling through the Vp, we have observed that positive terminal comes first. So, we have written it plus Vp, then VL was negative, then VAP was positive equal to 0. So, we have got the voltage across the inductor will be equal to sum of the input voltage plus the reflected output voltage. Vp is nothing but the reflected output voltage. Okay. Now, in mode 2, again applying the KVL in the same way. Okay. So, we will observe that now in this case we will observe that the primary side voltage and the reflected secondary voltage, that is VAB, which was we have obtained after eliminating the bridge and the reflected secondary bridge voltage, that will be cancelling out each other and the inductor will be experiencing 400 minus 400. So, it will be equal to 0. So, in this case it is equal to 0 as per our example. So, what will happen to the inductor current in this case? It will be maintained constant because there is no net voltage applied across the inductor. So, the current will be maintained at its same value. This was the value at the start of the cycle, that will remain constant for this mode of operation. Okay. So, for mode 1, it was experiencing positive voltage. So, it has increased. Now, after that in mode 2, it will be maintained constant. Now, in mode 3, again we apply KVL in this direction, I will observe that all 3 of them will be negative. Okay, because all the negative terminals are coming while traveling in this loop. So, minus now VL will be equal to minus of VAB plus the reflected second side voltage. So, in this case it is equal to minus of 400 plus 400. So, 800 volts will be applied across this. So, it will be experiencing and minus 800 volts. So, the current will start decreasing in the mode 3. Okay. So, as the duration is delta t, if you see the duration for which mode 1 is applied, it is 45 degrees. Similarly, mode 3 it is applied with delta t duration. In the first case, it was having plus 800 as the driving voltage. In this case, it is having minus 800 as the driving voltage. So, the slope will be equal and opposite. So, the value and the starting points, if you see, the starting point over here and the ending point over here are equal and opposite in magnitude. So, that is why it will again come back to the same minimum current. Okay. So, because the time is same and the voltage which is causing this drop or increase in the current is same. So, they will end with the same values, start with the same value and end with the same value. So, it will come back to I minimum point which is marked over here. Okay. So, after the mode 3 we will go into mode 4. Okay. So, in this mode 4 what has happened now, we had the switching on the secondary side bridge. Okay. Because of that the equivalent circuit has changed to the fourth option over here. Now, even in this case when I apply KVL, I will observe that the VL will be equal to minus VAP plus VP. So, minus VAB plus VP minus 400 plus 400, again they will cancel out each other and it will become equal to 0. So, 0 voltage is applied across the inductor. So, it will maintain the current as it is. So, it was at the minimum value or the negative value, it will remain constant for the mode 4. Okay. So, now in this case what we have done till now, first we have eliminated the primary side bridge, then we have eliminated the secondary side bridge, then we have eliminated the transformer, then we have found out what will be the voltage across the inductor, and assuming it starts from the steady state value, that is negative finite value, we have drawn the waveform for IL. Okay. So, that completes the first task to find out the waveform of IL. Now, the second task, that is to find out the output current or the I2 current. Okay. So, the load current, how to find out the load current, as we have discussed multiple number of times, we can find it out from the dot convention or from the conclusions. Okay. So, we will go ahead with the conclusions. When S5 and S8 are on, I2 and IL will be having the same shape. Whenever S6 and S7 are on, I2 and IL will have the opposite polarity. Okay. So, with that conclusion in mind, we will try to find out I2 as we have already found out IL waveform. Okay. So, for these 4 divisions S5 and S8 are on. So, for these 4 division I will maintain the IL and I2 in the same polarity. Okay. So, here if you see it was positive. So, for this 3 division it is positive. So, it is reflected as it is. In this case in the 4th division it was starting from negative and it becomes, sorry, it starts from positive and it becomes negative. So, that is what is maintained over here. So, whichever is your IL waveform, that is same whenever S5 and S8 are on. For the remaining divisions, for the last 3 divisions, suppose here in this case S6 and S7 are on. So, I2 and IL will have opposite polarity. So, here it was negative, so it becomes positive. Okay. In this case it was starting from negative finite value. So, it will start from positive finite value because it will get flipped and we will get the I2 waveform with this shape. Okay. So, how we have found out this? From our conclusions which we have derived by analyzing the circuit in a simpler way. Okay. So, that holds true whenever we are going into the actual loading condition. So, this now we are done with the second task of finding out the I2 value. Okay. So, first we have found out IL, then by using our conclusions we have found out the I2 which is the load current. Now, from this graph what will be the power being transferred to the load. So, now we have to find out the average value of this current. Okay. So, when I go for calculating the average value, I will see that these areas which are marked in green color, they will be cancelling out with the areas which are marked in yellow color, because they are having equal and opposite area. So, they will cancel out each other and the net power will be transferred because of these 6 divisions which are having the constant current. Okay. So, the slope region does not participate in the power transfer. Whenever the current is constant, they will participate in the power transfer. Okay. So, what happens in this slopy region? For 50% of the time we are drawing the power, for 50% of the time we are giving back the power. So, it just circulates inside this. Okay. So, sometimes the current which is flowing in this region is called as circulating current, and the power transferred is 0 in this case. So, we can call that as reactive power also, which circulates because of the phase shift which is created in across the transformer voltage Okay, so the voltage across the transformers has an phase shift of delta. Because of that, we get this reactive power component or circulating current, because it is not participating in the power flow. Okay. So, this is an unwanted current for us. So, the currents which is flowing into highlighted divisions are unwanted currents, and 50% of this value, that is, if I integrate the yellow region, I will call that as back power, or the power which will be transferred during this yellow region portion, I will call that as back power. If I integrate the entire duration, I will get a net 0 value. Okay. So, we have to consider the negative portion, which is generally called as your back power. In this case, both positive and negative regions are same, but when we go for the actual loading, we will see that they will not be same. So, the negative region will be representing your back power. Sometimes it is called as back flow power. So, it is the same meaning, that is, it is not participating in your power transfer. We were trying to force the power from the input state to the output stage in this case, but due to this slopy region, the power is again flowing back to our source side. So, that is why it is called as back power. Okay. And this slopy region does not participate in the power transfer, because the area is equal and opposite. So, they will get cancelled out when I find the average value of I2. Now, let us see how to find out what is the actual power which will be flowing by integrating the current graph now. So, here in this case is I2, we how to find out the power? We can either integrate I2 and multiply with V2, or we can integrate IL multiply with V1. Okay, why? We are assuming lossless circuit, and IL, it is assumed to be on the primary side for our analysis. So, I can just find out the IL value multiply with V1, or I can find out the I2 value multiply with V2. I will get the same power, because input power will be equal to output power, as we have neglected the losses. Okay. So, let us go with the first case, where we will be finding out the primary side power, or the power drawn from the source. Okay. So, for that IL, so it is the same representation of y equal to mx plus c equation, because this is a straight line. So, now the inductor is given with an voltage of this much. So, that will be the slope of the line, that is VAB plus VP by L, that will be the slope of the line. The variable over here is the time, which is written in the small t. Okay, minus this I max is nothing but our initial condition, which we have assumed that the current starts from finite negative value. Inductor current starts from finite negative value, as shown over here. Okay. So, because of that, we get this equation. So, where this equation will be valid till mode 1. What is our mode 1? Till this delta t time, 0 to delta t time, my mode 1 will be valid. So, if I replace the instantaneous time with t1, that is the end of my cycle. So, if I mark this as t1, so during this time, what will be the current? Okay. So, how to find it out? In the instantaneous value, I will replace it by t1, which we have assumed at the end of mode 1, which is equal to delta into t, where t is the switching time period. Okay. And delta is our shift angle, which we have assumed 45 for our example in this case. Okay. So, it can be any arbitrary value. In the analysis, we can replace just the value which we have considered, maybe 30, 35, any value as for the required power flow. Okay. So, here delta t, now we will get the final value of current in the mode 1, which will be the maximum current. We know that that will be maximum, and it will be an positive value. Okay. So, I can find out the current IL at the time instant t1 by using this expression. Now, moving to mode 2. Okay. So, in mode 2, what will be the voltage applied across the inductor? It will be the difference between our VAB and VP, and that will be divided by L to find out the slope of the line over here. Okay. And added with the initial value, that is plus I max, as the at the end of mode 1, or at the beginning of mode 2, it was at I max value. Okay. So, here why we are not replacing it by 0, because this is a generalized calculation. Okay. So, these calculations will be valid even if we do not have the rated values at the terminals. Okay. So, we will see what happens when we do not have rated values across the terminals, and why we will not have that condition which we are assuming over here. So, we will see that in the next example. Okay. So, here AB is assumed as VP. So, the slope will become equal to 0. So, in this entire mode 2, the current will be fixed. It will be at an value of I max. Okay. Now in mode 3. Okay, so in mode 3 what will happen now? We have already found out that the voltage will be equal to VAB plus VP by L with a negative sign, because now the inductor is experiencing negative voltage, it will start decreasing, and the initial value of the current is maximum and positive. Okay, so this is the initial value which is I max. Okay. Now IL3 will be equal to T3 will be equal to I max minus of 2 times of VAP. Why? We are assuming that we are having the nominal loading condition, that is VAB is equal to VP, or the reflected primary terminal voltage and the actual primary terminal voltage are same, or the voltage across the inductor are same. So, we are just replacing that, and that will be giving me the 2 times of VAB, or I can write 2 times of VP, or 2 times of V2 by N. Okay. So, that also can be replaced over here. Okay. So, here now T3, what will be the value of T3 now? So, let us see from the time stamp. So, it is delta T, then it is T by 2 50% of our cycle, then it will be T by 2, this point will be equal to T by 2 plus delta T. Okay. So, what will be the end of this or T3 duration over here? T3 will be equal to T by 2 plus delta 3. Okay. So, because this is my half cycle, that is T by 2, and this mode 3 starts from the end of first half, and it is valid for one division. So, which is delta T time. So, T by 2 into delta T, that will be my T3 value. When I replace that, I will be able to find out what will be the current at the end of mode 3. Okay. And when I replace the actual values, I will observe that it will become equal to minus I max. Okay. Now in mode 4. Okay. So in mode 4 what will happen? Now the voltage across the inductor will be minus VAB plus VP, and the slope of the line will be minus VAB plus VP by L, where these two will be cancelling out each other, and we will be left with 0 values if we have nominal loading condition. Okay. So that will be the current will be maintained at constant value, that is at minus I max in this mode 4. Okay. So, they are cancelling each other, and at the end of the cycle, if I mark this point as T4, that is the end of my entire cycle. So, it will be equal to minus I max value. Okay. So, because it is maintaining constant for the entire mode 4. Okay. So, now what we have done, after we have drawn the waveforms for IL and I2, we have integrated it to find out the instantaneous current through the inductor IL, because we are trying to find out the input power or the power drawn from the input side. Okay. So, now let us go for the power. Now, we are done with the calculation of the instantaneous current. Now, we will find the power, average power which is flowing through it. Okay. So, the average power, if you see, the waveform is perfectly symmetrical if you consider the half cycle over here. Okay. So, let us consider the half cycle. Okay. So, in this is my half cycle. If I see the current waveform on both the sides, we will see that it is having symmetrical shape. Okay. Or if you see this waveform, it will be pretty clear from the I2 waveform. Okay. So, if you see, it is exactly same, or it is repeating after half cycle. So, we can just integrate or find out the average value for an half cycle, it will be same for the average value for the entire cycle. So, the other way around, if we want to verify it by ourselves, so I can replace the integration with 0 to t or divided over the entire cycle time. Okay. So, both will be giving me the same answer. Okay. So, here we are assuming that the integration is done for the half cycle, and we are dividing it by 1 by t by 2. So, it becomes 2 by t. Okay. So, now V input, that is my V1, now it will be IL. Okay. So, that will be giving me the power which is drawn from that integrated over the half cycle. I will be able to find out what is the power being drawn from the source side. The same power will be given to the load as we are neglecting the losses. Okay. So, now in this half cycle, if you see, we have two modes, that is mode 1 and mode 2. Okay. So, now we have split this integration into two parts. Mode 1, what was the time limit for mode 1? It starts from 0, it ends at delta t value. Similarly, the mode 2, it starts from delta t and it is valid till the end of my half cycle. Okay. So, in this way we have split the integration into two parts, from 0 to delta t and from delta t to t by 2 or end of half cycle. Okay. And the input voltage is V1. Okay. So, that is what we have replaced. So, this will be constant for multiplied for the entire integration. So, now we have split it into two parts and we know the values of IL for each of this mode, which we have just calculated. We will just replace that and integrate. When I solve that, I will find the expression for average power given as 2 V1 square delta T by L multiplied with 1 minus delta. Okay. So, here we should keep in mind that delta we have defined as the shift by the entire time period. Okay. So, in some cases or in some analysis, we will find that the delta will be defined with respect to the half time period. Here we are defining it with respect to the entire cycle, that is from 0 to 360. Okay. So, that has to be kept in mind while replacing the values of parameters in this calculation. Okay. So, we have assumed it is given by shift by 360 degree or the entire duration. Okay. So, that is what was our assumption throughout the analysis. So, that is what has to be replaced over here. Okay. So, what is our observation now? The average power, if you see, it is then function of delta and the inductor, which we have already seen while going for our analytical study. We have seen that it will be depending on the inductor size, the power flow will be dependent on the inductor size. That is what is same conclusion is seen from this expression. But once the transformer and the DAB is designed, only variable which is left with us is delta value. Okay. So, it has 1 degree of freedom. So, we will see what is the use of degree of freedom when we go for our further analysis. Okay. So, this is the power flow through an DAB with respect to any given delta value, and if the other parameters are known, we can find out the power which will be transferred from the source to the load end. Okay. Now, let us go for actual loading condition. Okay. Why the previous case was not actual loading condition? Because in electric vehicle applications, we will always have battery bank on one side. When we see the charger, the load end will be our battery bank of our electric vehicle. When I go to the onboard electronics, the source will be my battery bank and the load will be an electric motor which will be driving the vehicle. Okay. So, when I have battery bank, we have already discussed that the battery bank voltage will be variable based on its charging level. Okay. So, if the SOC is higher, the terminal voltage may be at the rated value. When the SOC is less, it will be decreasing by some factor. Okay. So, in this case, we are assuming that the battery bank is discharged not at the nominal condition. So, what will be the operation of DAV when we have such scenario? Okay. So, in the same example where we have considered the input voltage to be 400, now we are assuming that the output stage voltage has decreased from 800 to 750 and the other parameters are the same. We will again assume the delta to be 45 and the mode of operation or the control technique is assumed to be single phase shift control as usual. Okay. Now, what has changed from our previous analysis? As delta has kept constant, now we will see only the main difference which will occur now. So, whenever the bridge is eliminated, in the previous case we were getting plus or minus 800, in this case we will get plus and minus 750. That is what will be the change when I eliminate the secondary side bridge. Now, voltage has decreased from 800 to 750. Okay. So, the same 4 modes, because we have assumed the delta to be 45 over here, delta is again assumed to be 45. If you see the phase shift between the primary and secondary side bridge pulses, they are separated by 45 degrees. So, the same 4 modes will be there. For the first division, this equivalent circuit will be valid, where the output stage, if you see S6 and S7 are on, so it will be minus 750. For the next equivalent circuit, it will be valid for mode 2, where S5 and S8 are on the secondary side and S1 and S4 are on the primary side. So, on the primary side we will get the plus 400 volt, on the secondary side as S5 and S8 are on, instead of plus 800 we will now get plus 750. Okay. For the mode 3, again we will get plus 750 because there is no change on the secondary side bridge, but on the primary side if you observe we have shifted the pulse from S1 S4 to S2 and S3. So, the primary side voltage will become equal to minus 400 when I eliminate the primary bridge. Okay. Now, the mode 4 in this case, if you see we have now switched back to our S6 and S7 on the secondary side, whereas the primary side still maintains with the S2 and S3. So, primary voltage will be still at minus 400 and the secondary side voltage will become minus 750. Okay. So, after that what will be the next step? Now, we have eliminated the primary and secondary side bridge. Now, we will find out what will be the reflected voltage as we are assuming the leakage inductance to or the external inductor to be connected on the primary side of the transformer. We will find the reflected secondary voltage on the primary terminal, so that we will be able to find out what will be the voltage difference across the inductor. Okay. So, when I do so, what will happen? Now, the transformer turns ratio, once this circuit was designed with 1:2, so it will remain as it is, because with the SOC there will be no effect on the transformer turns. So, now, the 750 which was reflected as 400 in the previous case, now it will be 750 by 2. The reflected voltage magnitude will decrease from 400 to 375 because the output battery bank is now no longer having the full SOC. So, it is discharged. So, it is having lower voltage. Okay. So, now what will happen? What changes will be observed when we have in this condition or when we see this type of loading to the DAB. So, if I apply KVL in this loop now, in the same way which we have done in the last discussion. So, I will observe that the voltage will now be equal to the addition of, in the mode 1 it will be equal to the addition of V A plus the reflected second side voltage, that is V P by L. Now, instead of 400 into 2, that was 800 in the previous case, now the slope will decrease to somewhat other value which will be equal to 775. Okay, because 775 by L, that is what will be the slope of this line. In the previous case it was equal to 800 by L because there was nominal loading on the both the ends. So, in this case now, although the expression is the same, but the voltage will be decreasing, that will be resulting in the change in the slope. Now, the initial current, that is we are assuming it to start from the maximum negative value. At the end of this mode 1, in the previous case it was reaching to the maximum positive current value, whereas in this case it will not be able to reach that value because the answer lies in the next mode, that is in mode 2. In the previous case, what was the voltage applied across the inductor in mode 2? It was equal to 0, but whereas in this case when I apply KVL in this equivalent circuit which we have derived by eliminating the transformer, I will observe that it will be subjected to an voltage which will be equal to the difference between the two voltages, which is equal to 25 volts in this case, because it 400 minus 375, it will be giving me 25 by L. So, I see that in mode 2 also we have an small positive voltage which is being applied across the inductor, whereas in the nominal loading condition it was perfectly balanced. So, they were cancelling out each other and we were getting 0 voltage. So, there was no slope, or it was meant current was constant through the inductor, or the inductor current was constant because of 0 driving force, whereas in this case inductor is having a positive voltage. So, it will be experiencing rising current as positive voltage is applied. So, it will start charging. Okay. But what will be the slopes? If you see, the slopes will be pretty different from the both the modes. Mode 1, the slope was very high because both the voltages were adding the current increment, whereas in this case the difference between the two voltage is adding the current increment. So, the slope is very less. So, if you see, the current rises gradually in this case because of less driving voltage. So, at the end of mode 2, now it will reach to the maximum positive current value. So, what changes has been observed in the case 1, or in the mode 1, where it was experiencing 2 times of the supply voltage, now it has experienced somewhat lower voltage, and in mode 2 where it was experiencing 0 voltage, it is experiencing somewhat positive voltage. Similarly, when I go into mode 3, I will observe that it will be experiencing the same magnitude of voltage, that is 775, but in the opposite direction. So, the current will decrease and it will reach to an intermediate value, it will not go to the maximum negative value as in the previous case. Now, when I go into mode 4 and apply the KVL, I will observe that it will be equal to minus 25 by L, okay, because minus VAB, which is 400, but BP, or the reflected second side voltage, has become 375. So, net 25 volts will be applied in the reverse direction. So, the inductor will start discharging further, or the current will be increased in the negative direction. Okay. So, it will go to the maximum negative value at the end of the cycle. Okay. So, that is what was the starting point for us. Okay. So, what changes we have observed in this waveform? When the DAB is going for actual loading conditions, where the voltages will be different than the desired values, the inductors will be continuously charging and discharging. There will be no zero voltage application across the inductor. So, mode 1, it will be charging with a slower rate compared to the previous case, where the nominal voltage were there. In mode 2, previously it was maintaining the constant current because zero voltage was applied, whereas in this case, as the difference between the two is not zero, the reflected primary side voltage and the actual primary or the source voltage will get some finite value. So, it will start charging, and in the mode 3, the similar observations will be repeated with negative polarity. Okay. So, we will stop at this point. So, in this lecture we have seen the nominal operation of DAB when rated voltages are connected at both the ends of the DAB. Then we have seen the actual loading condition, where the output voltage or the input voltage can have some difference in the value compared to the nominal values, and we have seen the operation and what changes will be there when we have such a loading. That is what we are discussing now. We will continue from this point in the next class. Thank you.